Okay, welcome back to CS353 Makeup Week. We're going to be covering Chapter 10 right now, which is Physical Memory and Physical Addressing. So, let me just get this full screen. This is a chapter that covers mainly what we think of as, commonly as random access memory, RAM. RAM is a volatile substance. In other words, if you end up turning off the power or something like that, it goes away. It's not a permanent type of memory as you see in ROMs, for example, or even storage devices. So it's definitely volatile, and there's two basic technologies that we'll look at when considering this, which is static RAM and dynamic RAM, and basically we'll talk about the differences of these shortly. So static RAM is the easiest to understand. It's similar to a flip-flop. You just basically tell each bit that it's either been written on or it hasn't been written on. There's a write that comes in, and what comes out is the actual value for the bit. So there's a circuit for the bit, and there's a write enable that comes into it, there's an input that comes in, and it can either turn it on or off. That ends up looking like this. So basically, if the enable bit is high, the output is the same as the input. So in other words, if output is or if the enable bit is set to a high value, then we will write to it. Otherwise, it will hold the last value, so it'll just do a read. It'll simply read, the input will come in, say that it wants to read it. The enable bit will be set to low value, and it can just read from whatever was previously there. So in other words, when write enable line is on, it records that input value. If it is off, the circuit holds the same value. So this is the idea of a read and write, basically, on the static RAM. This is a fast type of RAM. It can, doesn't require a refresh either, which is what we'll talk about with the DRAM. The refresh circuitry is some extra circuitry on top that's required by DRAM but isn't by SRAM, because basically SRAM just simply tells you whether it's on or off. Because of the fact that it's always maintaining the bits, it is highly expensive for power consumption. For that reason, a lot of times, even though given the complexity of DRAM, often the times that's chosen. It's also a high cost because it has to have circuitry that maintains those bits, and a much higher cost than DRAM. So DRAM is the alternative. It consumes less power. It's basically taking advantage of the way the capacitor works, and taking advantage of the fact that the capacitor is gradually going to lose its charge, and basically working around that physical property, we can actually make a system that still holds values even though it's gradually losing its charge. So the fact that it isn't keeping its charge means that it's holding less power, therefore less heat, less power consumption, and we just sort of let it gradually lose its charge. So as we know, with sort of the way electronic circuits work and electricity, as entropy increases, any storage device is gradually going to lose its charge. So when left for a long time, DRAM is eventually going to change from a logical 1 to a logical 0. That can be less than a second. Therefore, although it's inexpensive, it's really an imperfect memory device because you can't tell how long it's going to actually hold that charge. So the creators of DRAM needed to figure out a way to make this work. And basically what they said was, why don't we just repeatedly step through the DRAM and read the value from it, then write it right back to it, and that's what we call a refresh circuit. So immediately after reading from the DRAM, we write right back to the same location. So we're effectively recharging that memory bit. So reading from it and then writing right back to it. And that's what it looks like by illustration. This is on page 145. So it basically comes in and it will go out right away, and then the next tick it's going to refresh this circuit. So it's going to be constantly refreshing. So some circuitry is going to be needed for that refresh bit that isn't needed in the SRAM. Of course, it's more complex than this. You have to coordinate the read and write direction, read and write operations accordingly, and you need to have this for all your bits in memory, not just one. So you need that refresh circuitry for each given bit. So there's some complexity that arises there, but it's still going to be less power than the SRAM keeping that charge forever. A couple things we think about when we think about memory technology is the density of the memory, the number of memory cells per square area, basically, of the silicon chip, and what the latency and cycle time is. So as I mentioned, one sec here, one sec. So when referring to the density, we want to talk about the basically the number of bits on its standard chip. So 4 meg chip holding 4 megabits of memory, for example. This is just basically how much memory is on each chip is basically just what this is referring to. Obviously, if you have a higher density chip, if the cells are closer together, it's going to dispense more heat. And basically the density of these chips is related to the size of the transistors, which in general has followed Moore's law. So we're seeing that density is doubling every roughly year and a half. Latency is another factor in looking at how to measure memory, and that is basically looking at the time that elapses between the start of operation and the completion of operation. And it's not constant, so latency is generally something that we use to measure how good the memory, or how effective the memory is, how optimal the memory is. And I'm going to pause for a moment and let you continue here and to the next video. This gets us up through page 146, and the next video will continue from there.